It's 11:02 and 19 seconds on the 24th of June. I'm here working on number 8 and number 28. I previously thought that these two were mirror images of each other, but I'm wrong. I didn't look at them that closely. You can see number 8. Here's my knot diagram without the notation. We start here, we go around, we go across into a loop, back down, around, over, and back to the start. That's slightly different than number 28, where you can see we do the same loop, but we go this time on the far side, over and down and into a loop and back down. If we look at number 8, they're the same, except for the loop is right here. Here's the graph, and this is number 8. And in number 28, the loop comes up this way and goes into the loop. The colors are almost identical. On the outside and the inside, we have white and white. We have black and black. The colors just differ on the inside right here. They're black right here, black right here. But on the graph, we have white and white across and black, but black and black across and white. On number 28, we have black and black with white across. And in the reverse, we have white and white with black across. On the right-hand triangle, here it's 2 whites and a black. But on the right-hand triangle here, we have the 2 blacks and the white. The knot notation is right here. It looks very similar. If I lay it, the knot notation starts in the same vertice. It's the top vertice right here and right here. We go this way. It looks very similar. If I lay the knot notation next to each other, the crosses, the blocks are unders. They look like they're frame shifted, but what they're actually are, they're opposite. So we turn it upside down and do it backwards, you can see the knot notation is reversed. So these are 2 very similar solutions that are almost identical. They vary very slightly, and each one of these has a mirror image. Not exactly a mirror image, but the same solution, but with the black and white surfaces swapped. I have yet to find those solutions, and we have a lot of solutions. We have all of these to go through. I don't know how many solutions there are. I found a few pairs, but it takes a lot of time to examine the knot notation and the graphs. But one thing they have in common, they all are 6 vertices, and they all have a Eulerian circuit that has 6 vertices, 12 edges. They all share the same connectivity. And as you might remember, these are Mobius strips, or they were once Mobius strips, that were given 3 flips and cut down the middle. I'm going to pick up my favorite one. There's a few perfectly symmetrical solutions. This one here is my favorite. It's very symmetrical. There's a few more interesting ones. You can see here, here's the overhand knot. There's 3 twists. But here, this loop has jumped from here over to part of the knot here, or instead of it being right here on the bottom, it can jump into the curve, which would be right here, or it can move around further. This loop that was right here, it can jump up to right here, and here's this solution. The loop has gone from here up to here, or it can jump over to here. In this solution, here's the loop right here. It's gone from right here up to right here. So there's patterns that are emerging, and here we have a mirror pair, I believe. We have a loop on the bottom. We have, so these are a copy of each other. We have a loop on the side, and the knot notation comes in, around, up, and down. And again, you can see here it comes in, around, up, and down. I'm pretty sure if we look at one crossing, here the horizontal is in the over position. The horizontal is in the over position. So I'm pretty sure just looking at those two that they're just a copy. I found the same solution twice. Unfortunately, I did these first without my Mobius paper, so we're lacking 2 pieces of information. We're lacking the colors of the edges. See, they're both blank, and we're lacking the edge notation. We don't know which is edge, but this one unfortunately does have the edge notation. You can see the black squiggle on the bottom, so that's the same edge. But here's with my standard Mobius paper. We have the edges separated, the bottom edge of the black line, the top edge which is blank, and the surfaces. Here's a black surface, and here's a white surface. There's a lot of work to be done to figure out the symmetries. Unfortunately, the equation to work out how many solutions there are in graph theory. The Eulerian circuits is very complex. I don't know if it's going to yield to my work. And I've gotten away from the paper solutions for a while for obvious reasons, because the wife gets really annoyed when they all come out of the boxes. But tonight I've gone back to the paper solutions to try to match them up, and I've gotten stuck on these two. It's taken a while. So we'll plow on through it. And these guys, I don't know what category they're falling in. They're just all very strange. This one here is particularly beautiful. It, as you can see, has an outer boundary that's just, there's one edge here, and there's one edge here, there's one edge here. There's three edges, and most of them are black. They're all black here. They're black. This edge here is white. And there's two loops on the inside. You can see there's a loop here, and there's a loop here. And they both have a black plane on the inside of their loop. That one's particularly nice. He's number 19, counterclockwise version. If we did the clockwise version, we would find the same thing as the mirror image with the same shading for the surfaces. At least I think so. I might actually go and look for the solution as a task to prove that hypothesis. That's it. The time now by exact UTC is 10:08 and 53 seconds.